Does not change. Right, so the velocity at a point does not change. So if I have a pipe or whatever, and I have fluid flowing through that pipe, I take a particular point, and I ask myself, what is the velocity at that point? And in a steady flow, the velocity at that point is going to remain constant. In unsteady flow, it's not going to be constant. Steady flow. So that's one of our characteristics. In a study of an ideal fluid, it would be which of these, steady or unsteady? What do you think? Somebody said it. It's steady, right? So in an ideal fluid, we're going to be looking at steady flow. And we'll consider all of our fluids ideal. The second one is rotational or irrotational. Can I go down from here? All right. So the second characteristic that we'll look at is it rotational or irrotational? All right, so a fluid that is irrotational will be like what we had before, where it is just flowing along in a straight line. So the irrotational fluid flows in a straight line, or flows without rotation, we'll say. It doesn't have to be a straight line necessarily, but it doesn't rotate, right? And rotational fluid flows with rotation, right? Can you think of a fluid that has rotation? The washing machine. That's a much cleaner example than I was thinking, but the toilet is a good example of rotational fluid, okay? I'm sorry to put that in your mind, but next time you go to the toilet, I want you to think about what is this rotational or irrotational, okay? I know that's not appropriate, but it's a good example of rotational fluid because you have this fluid that's rotating. All right? So rotational or irrotational. Which of these is going to be our ideal fluid? In ideal fluid flow, it's going to be which, do you think? Irrotational. So far, ideal fluids will have steady flow and will have irrotational. Constant velocity, and it doesn't go in a circle. The third thing is viscous or non-viscous. And we'll take a little detour with this and just sort of sit here for a bit. Viscous or non-viscous? You probably know what viscous means. Can you tell me a fluid that is viscous? What? Oh, blood is viscous? Yes. So that's not what usually comes to people's mind. But what do you think? Another? Okay, like pancake syrup. Yeah, so pancake syrup or molasses, that's very viscous. We'll talk about blood and how it's viscous and why that's important in the flow of blood. Maybe today, maybe Thursday. All right. So viscosity, a viscous fluid, this results from friction between the molecules for a viscous fluid. So literally, they rub up against one another, and it causes them to flow at a slower rate, the greater viscosity. And so some examples of more viscous fluids are like, say, for example, I gave you three fluids. Actually, here, I'll do it as a question. I'm going to give you a series of fluids. 1, 2, 3, 4. Let's say molasses, water, air, and blood. And I want you to rank these in order of their viscosity, from least to greatest viscosity. All right, and I'm going to go and introduce this variable for the viscosity. Let's see, I think it's eta that we use. Yeah, we're going to use this variable. It looks sort of like an N, but it's the Greek letter eta. Looks like that. So I want you to rank these from least to greatest viscosity. And I'll give you some options here, but you can go and start thinking about it. Let's see. From least to greatest viscosity. Is it 2, 1, 4, 3? Is it 3, 2, 4, 1? Or is it 4, 2, 1, 3? Just a second, I'll open it up. So rank these in order from least to greatest viscosity. Remembering viscosity is a measure of how slowly does it flow. The least viscosity, least viscous to greatest viscosity. About 10 more seconds. I'll stop at 35. B is right. So the least viscous of these obviously is air. Right? Air has basically no friction between the molecules because the molecules don't actually touch. In a gas, in an ideal gas, the molecules don't interact with one another. The next is water, 2. And then I was sort of guessing, but I'm assuming that blood is less viscous than water. Is that true? Or is more viscous? It's more. That's why I said, yeah, more. I said less first. I meant more. And then molasses is the most viscous of all of these. Okay, so that's from least to greatest viscosity. Viscosity usually increases with lowered temperature. But that doesn't have to be the case. You've probably witnessed this, like if you have something that's a fluid, but then you put syrup, for example, if you put in the refrigerator, it's just going to come out more slowly when it gets cold. So you know this sort of experientially. But it doesn't have to be the case. There are certain fluids called superfluids. I don't know if this is in your book. Do you remember reading about superfluids in your? It is in your book. Okay. Certain fluids called superfluids. No, this is still under viscosity versus non-viscosity. We're going to sort of camp here for just a few minutes. So superfluids are those with no viscosity. And this occurs at near zero temperatures. And when I say zero temperature, I don't mean like, oh, it's 0 degrees outside. I mean the lowest temperature, the absolute zero temperature. Y'all probably heard of this before, right? We have these different temperature scales. We'll get into these in a chapter or two. These different temperature scales, and they all go down to the lowest absolute point. And we refer to absolute zero, which is in, does anybody know that scale for temperature? No, not Celsius. The Kelvin scale, thank you. We'll get to that in a couple of chapters. But the 0 Kelvin is what we call absolute zero. And once you reach that point, all motion of atoms cease. So even like the vibrations of the electrons inside the atoms would stop. And so that's a theoretical temperature. You can't really get to it. But you can get pretty darn close. With liquid nitrogen and liquid helium, you can get down to just millikelvins above absolute zero. And a really cool thing happens when you have helium. It becomes a liquid at 0 degrees, and it becomes a superfluid. And if it has no viscosity, what is the implication for that? Do you know, it's basically viscosity when you have a container, like a glass of water. It's basically viscosity at its extreme that holds the water inside the glass because there's friction between the water and the glass molecules that doesn't allow the water molecules to go past the glass molecules. That's friction, basically. I mean, that's an extreme version. So what do you think if we had a superfluid that had no viscosity whatsoever? between any molecules, what would happen to your water in the glass? It would what? Right, it would just fall out the bottom because the water molecules wouldn't experience any friction with the glass molecules, and they would just drop out through the bottom of the glass because there's no viscosity. And so that's a superfluid. Let's watch this little video where they talk about, I think it's a BBC video, where they talk about this helium and how it becomes a superfluid. And then in the end, they'll actually show this where it actually begins to leak out of the container. Not because there's a break in the container, but because it's become a superfluid and all viscosity is ceased. And so it's like the container's not even there. It just starts to go through it. This experiment called the pitch drop experiment. And if you look at pitch, I don't know if y'all have ever seen pitch. I hadn't, never seen it in real life, but I think it's like a type of tar that's become really hard. Anybody seen pitch in real life? Yeah, I haven't. Well, it's like a rock, right? So it looks like a rock, this really dark, shiny block of rock, but I think it's really tar that's been hardened. I don't know, many decades ago, this scientist in, I think, Australia decided to see if there were fluid-like properties of this seemingly solid material. And so he took a beaker like this, like a funnel, and he put some of these blocks of pitch in it, and he just left it for many, many years. And they found that over time, that this pitch, that it would eventually flow through the funnel. And just in the past year, so over time, you get this pitch, and it sort of forms to the funnel, and then slowly it oozes out. And about every 80 years or so, you'll get a little drop. And that drop will fall down. And just this past year, we had a drop from the pitch drop experiment. Do y'all want to see it? Okay, it's kind of neat. This came up with Pascal's principle, and that is a fluid is either compressible or incompressible. Let's try a question, actually. See if you can jog your memory about Pascal's principle. Which of these was true in order for Pascal's principle to hold? Does a fluid have to be compressible, or does it have to be incompressible for Pascal's principle to hold true? And we'll let A be compressible and B be incompressible. Remember Pascal's principle, the principle behind hydraulic lifts? Does it require that the fluid be compressible or incompressible? Pascal's principle requires it to be compressible or incompressible, the fluid. I'll stop at 45. Okay, yeah, it is B. Remember, for Pascal's principle, it said that if you apply a pressure to a liquid or a fluid, then that pressure is felt all throughout that fluid. In order for that to be true, it has to be an incompressible fluid. But all liquids basically are incompressible. Water is incompressible. Hydraulic fluid, which is mainly oil, is incompressible. All right, so the definition then is when you apply pressure to a compressible fluid, the volume changes. When you apply pressure to a compressible fluid, the volume changes. Let's answer this question. Liquids are gases are compressible. I'm going to abbreviate compressible with a C, or compressible, compressible and incompressible. Incompressible and compressible are both incompressible. You'll follow what I mean? C means compressible, I means incompressible. To answer that question, fill in the blanks. Liquids are either compressible or incompressible. Gases are compressible or incompressible. What's the right combination? C means compressible, I means incompressible. All right, I'll stop at 45. 45. See, that must be right. Liquids are incompressible, gases are compressible, right? Which of these do you think, let's go ahead and write this in, which of these do you think compressible or incompressible, either A or B, is a quality of an ideal fluid? When we're talking about an ideal fluid, when we talk about the flow of fluids, which of these would be an ideal trait? Compressible or incompressible? We're talking about fluid flow. So remember we had steady so far, non-viscous. I had one other one. Oh yeah, irrotational. And now is it compressible or incompressible? Yeah. Yeah, so look, going along through all these traits, we've had ideal fluid flow is steady. Right. Ideal fluid flow is irrotational. Ideal fluid flow is non-viscous. All right. And now, is ideal fluid flow, is it a compressible fluid or an incompressible fluid? When we're talking about ideal fluid flow. All right, I'll stop at 115. 115. All right, B, right. It is incompressible, like blood, for example. We'll apply this to blood later on. It's incompressible. All right. And then the fifth thing, and the final attribute, is laminar versus turbulent. So this is the fifth characteristic. Is it laminar or turbulent? Non-viscous. Although there is we'll actually talk about that. So there is a range of viscosity. So is it laminar or turbulent? In a laminar flow, and this is typically how blood flows through the body, but the fluid flows in parallel layers. With no interaction between the layers, with no interaction. Between the layers. Now, the layers near to the sides of the pipe, I'll draw a picture in just a second. The layers near the sides of the pipe or whatever it may be, the artery or the vein or whatever, the sides of the pipe move more slowly. Because of viscosity. there a C or an S here in viscosity? C. Because of viscosity between the fluid and the pipe. So if I were to draw a picture of this, I have this pipe. Looks like this. It's stratified into different layers. So I have layers of fluid flow here, all the way through here. And if I were to break these up, let's say A, B, and C, where is the fluid going to travel the fastest? Where is the fluid going to travel the fastest? Will it travel at location A, which is near the side of the pipe? Will it travel fastest at B or at C? Where will it travel the fastest? Where will the fluid travel the fastest in this laminar flow? I break it into parallel sections because it says that in laminar flow, your fluid actually flows in these parallel layers. This is a cross section. I actually would be looking at cylinders of layers that would be flowing through this pipe. All right, I'll stop at 40 seconds. Where does it travel the fastest? Okay, C is right. So it travels the fastest in C. A is the slowest because it's sort of sticking to the sides of the pipe. There's friction between the fluid and the sides of the pipe. And C is the fastest, which is out. It's like out in the middle of the river, right? The middle part of the river is always the fastest. Right, so that's a similar thing. Also, just recognize that within this strata, within this parallel section right here, we have a constant velocity. Or a constant flow rate. Okay, that's laminar flow. It's broken up into these parallel sections that all travel at the same velocity. All right, that generally occurs. We generally think of blood flowing through the arteries and veins, at least as it gets further away from the heart, to be laminar. That it travels in this way, stratified in this way. Now let's look at turbulent flow, which is characteristic of what type of fluid flow in the body, or where is it turbulent, the most turbulent fluids flowing in the body. The what? Right, the heart. So in the heart, you have a lot of turbulence. You don't have this laminar flow. So turbulent flow. These layers they interact unpredictably. And the velocity of the fluid changes a lot. And this most often occurs in the heart. And we'll talk about the heart quite a bit. As blood flows between the different chambers, or rather as blood gushes between the different chambers. I don't think that's a technical term. I just made that up. It gushes, but it gives you a better idea of how it's flowing between the chambers. Okay? It's this turbulence that causes this distinctive sound when the heart is beating, and we'll talk about that in a bit. All right. I'll give y'all just a second. Move on from here, folks. Y'all see that in the back? All right, so those are the 5 characteristics. We had steady or unsteady, then we had rotational or irrotational, viscous or non-viscous, compressible or incompressible, and then laminar or turbulent. Of the laminar and turbulent flow, which of these is the characteristic of an ideal fluid flow? Laminar or turbulent? Right, laminar, right. So turbulent is very difficult to model mathematically, though it can be done, but it's very difficult to do so. All right, let's look at flow rate. And we're going to look at a couple of different equations. And, you know, as I said, on the exam, you might have some very simple calculations, kind of like you had on this previous exam. But more, I'll be looking at, with these equations that I give you, that you understand the relationships between the different variables. And once you get a hang of it, I think it's sort of intuitive. So we're going to talk about flow rate. Flow rate is just a measure of volume per unit time. So I have a certain volume of a fluid, whether it be water or air, gas, or liquid, that's flowing past a given point in a given time. What is my flow rate in volume per time? So I'm going to call this flow rate Q. We use the variable Q for flow rate. And it's equal to volume per time, we said. But let's say that I have a column. I have this cylinder. It has a certain volume, right? It also has a cross-sectional area here. That's like the area of that circle on the end of the cylinder. And then it also has a length, which I'll call L. All right. How is the volume related to the area and the length? Right, the volume is equal to the area times the length. Right, I could see that just dimensionally because the area is square meters, and then the length is meters, and then you bring them together and get cubic meters, or meters cubed, which is the unit for volume. So I can take this, and I can plug it in right here. So where I had volume now, I'm going to put area times length. I'm going to divide that by time. But here, if I have length over time, does that look like anything familiar to you? A distance over a time is a what? That's velocity, right? So I can describe my flow rate in volume per time, or I can describe my flow rate in area times velocity or speed. And that's a lot more useful. It's kind of difficult to measure a volume flow rate, kind of difficult to measure, you know, what is my volume of fluid moving through here in a certain amount of time. But it's fairly easy to measure a cross-sectional area and then measure the speed of the fluid inside, and that'll give you the same flow rate, which will be in the units of our flow rate. If you're in the SI system, we're going to be in meters cubed per second, by the way. So our Q then, which is volume per time, is also equal to my area times my velocity. That is my flow rate. And when you have an ideal fluid that's incompressible and all these things, that flow rate has to remain constant all the way throughout your system. If you have this closed system and there's no fluids coming into or out of the system, then that flow rate has to remain constant. Can you think of a good reason why that is? Why your flow rate has to remain constant? Why should your flow rate, if I have a closed system, why should the flow rate at any particular point in that system, like even if the pipes get bigger or smaller, why should the flow rate always remain the same? If it doesn't, it'll bust. Okay, I'm talking about an ideal fluid flow, so I'm not dealing with turbulence or any of that. Just think of water flowing through a pipe. Let me draw a picture. Maybe this will help. Let's say that I have a pipe, and that pipe gets bigger at some points, and it gets smaller at some points. So it looks like this. This says, if I'm saying that the flow rate must be the same, what I'm saying is that Q here has to equal Q here. It has to equal it there, and it has to equal it there. That flow rate always has to remain the same. Why is that? It's a simple explanation. Why does the flow rate have to remain the same? That's not really the answer I'm looking for. You might know. Let me open up the top of my head, and then maybe you can see the answer I'm thinking. No, it's because you don't have fluids coming into or out of, and so if I have a certain amount of fluid going past a point in a given amount of time, then that same amount of fluid has to go through another point in that same amount of time. You're not losing fluid. You've probably heard this law. It's called the conservation of matter. It just means that you can't destroy matter, basically. You can make it change forms or whatever, but you can't destroy it. And so this idea that the flow rate has to be the same just comes from this idea of the conservation of matter, that you can't destroy or create matter. You can only sort of change it between forms. And when we're talking about an ideal fluid flow, if the flow rate's the same, it's because you're not introducing fluids to the system, which would change the flow rate, and you're not taking fluids away from the system, which would also change the flow rate. You follow what I mean? Now, this brings up the flow rate equation. Your book calls it the flow rate equation. I've heard it more commonly called the continuity equation, but I don't think it matters that much. We'll just call it the flow rate equation. And it just says that Q at one point has to equal Q at another point. That my flow rate has to equal the same at different points in the system. And so it becomes useful because you can say, well, my flow rate is just A times V. So A1 V1 equals A2 V2. And this is the flow rate equation. Remember, because in the previous slide where we had Q as volume over time, we could transfer or change it to be area times speed, or area times velocity. So that is our flow rate equation. And this has a number of implications. Can I go on to the next slide? Yeah? All right, here we go. It has a number of implications. So if I have if I have a pipe and it gets smaller, like this, and this is my cross-sectional area, A1, and this is my velocity, V1. Over here, I have a cross-sectional area, A2, which is obviously smaller, right? What's going to happen to V2? Is V2 going to increase? Is V2 going to decrease? Or C, is V2 going to stay the same? What happens to V2? Does it increase, decrease, or stay the same? When the fluid enters this second section of pipe, what happens to the velocity of the fluid? Sorry. All right. What happens to V2 here when the fluid flows from here to this smaller section of pipe? What happens to the velocity in the second section of pipe? Does the fluid increase in speed? Does it decrease in speed? Or does it keep the same speed? In a closed system, yeah. Oh, this isn't our class coming in. All right, about 10 more seconds. I'll stop at 55. Like we're picking up another class. Get out of here, class. Okay. Oh, yeah. So what did y'all put? It's another class was clicking in. There's another class. What did y'all put? A? A is right. Very good. You can witness this like with a garden hose. You ever done this? Like if you squirt your brother or whatever with a garden hose, you put your thumb over the end, and you're changing which variable in the flow equation. When you put your thumb over the end, you're changing the area. You're making the area smaller, and if I make the area smaller, if this decreases, this has to increase in order to keep that flow rate equation correct. Right? So this is like a garden hose. You can try it later when you go home. You can squirt your friend or whatever with your garden hose and say, hey, it's the flow rate equation. And then they'll think it's really funny. All right, let's see. Let's look then at viscosity again. We've already talked about this a bit, but it comes up again. Well, I was supposed to show you that video here. I'm sorry. A little bit out of order. So we're going to revisit viscosity because it's going to come up and we're going to give it a more mathematical treatment of how viscosity affects the flow of fluids. And then we'll begin looking at blood, for example. So the viscosity of a fluid affects the flow. The viscosity of a fluid affects the flow. Remember the viscosity? Do you remember what variable we use for viscosity? It looks like an N, yeah. It's a Greek letter eta, which is my daughter's name. It's not spelled the same way, but that's my daughter's name. Ada, thank you. Ada is her name, but A-D-A. Ava? Oh, really? That's a pretty name. All right, so viscosity. The viscosity of a fluid affects the flow. How do you think it affects the flow? So if our viscosity goes down, does Q do which of these? Does Q go up? Does Q go down? Or does Q remain the same? So if eta, this measure of the viscosity, decreases, what happens to our flow rate? Does it increase, decrease, or stay the same? All right, I'll stop at 25. 25. Okay, very good. So which of those, the helium or the pitch, had a small viscosity? The helium had no viscosity, right? And so its flow rate, even though there was a container there, it flowed right through it, so it would have a very large flow rate. So A is correct. If the viscosity goes down, my flow rate's going to go up. Let me ask you some other questions about flow rate. You don't know these right off, but I think you can intuit them. What happens to my flow rate if my pressure differential increases? Now let me show you what I mean here. So let's say that I have a pipe here and I have fluid flowing through it in this direction. And over here, I have a big pressure. I'll call this P1. And over here, I have a little pressure, P2. And the difference in those is called the pressure differential, or delta P. So what happens if my pressure differential goes up? What happens to my flow rate? That is the difference between P1 and P2. If that difference gets larger, what happens to my flow rate? Q. What happens to my flow rate? I have a larger pressure differential. How does that affect the flow of the fluid? It's going from a large pressure to a small pressure, yeah. That's tend to how fluids flow, right, from high pressure to low pressure. All right, I'll stop at 45. I want to ask another series of questions here. We're trying to get to a equation. Okay, so the pressure differential goes up. I'm not sure y'all understand. Let me just explain. So the pressure differential means how different are they? So let's say that this was 100 pascals and this was 10 pascals. All right. Fluid's going to flow from what? High to low or low to high pressures? High to low, right. So move from high to low pressure. Remember, like with the straw, we created a low pressure inside the straw, and the fluid from the high pressure outside in the cup moved up into the straw. So fluids move from high to low pressure. All right. Now, depending upon the difference in those pressures will tell me how much like what's going to be the flow rate. How quickly is it going to move? So let's say I have 110 pascals. That's like 100 here and 10 pascals here. That's going to give me a pressure differential of what? 90 pascals, right? But let's say I make that bigger. Like let's say that instead of 100 here, I make this 1,000 pascals. And that's what I'm saying over here, that if I increase that pressure differential, that is, I increase the difference between this number and this number, how is that going to affect how quickly the fluid flows? Is that a little more clear? Let's try the question again, okay? I'm increasing that delta P. All right, I'll stop at 28. 28. How did you miss it? I'm sorry. That's okay. So A is the right answer. If that pressure differential goes up, it's going to increase the fluid flow, the flow rate. So good job, 15 of you. All right, now let's look at a couple other variables. So far we have Q is proportional to 1 over the viscosity. All right, that means if the viscosity goes up, the flow rate goes down. We also have that Q is proportional to delta P. That is, if the pressure differential goes up, the flow rate goes up. If you have a greater difference in pressure, the fluid's going to flow at a greater rate. And what happens if the length L, if L increases, what will happen to Q? Everything else held constant. If I just make my pipe longer, what's going to happen to my flow rate? Same amount of fluid, same pressure differential, same viscosity. I just make my pipe longer. What happens to the flow? Oh no, not same amount of fluid. That doesn't really come into it, but the same, how's it going to affect the flow rate? Because if I have a longer pipe, obviously I'm going to have more fluid in it, right? But how does it affect the flow rate? If the length increases, what happens to Q? All right, I'm going to stop at 45. What? Is it harder or easier? Let me think. What's it? Like when I was a kid, we used to run out of gas a lot, right? And my uncle, Mac D, his middle name is D, like the letter D. My uncle had a bunch of cars, and you could always go down to his house and you could get gas out of his gas tank, right? Because you get a hose, you ever do this, siphon gas out of a car? And then the gas comes out and you get a bunch in your mouth and then you got to put the hose into the thing. Well, is it easier or more difficult if you have a really long piece of hose to siphon gas out of a gas tank? It's more difficult, right? So if my length of hose gets longer, it's going to be harder to make it flow. So given the same pressure, what's going to happen to the flow rate? It's not C. Let's try it again. That's why whenever you siphon gas, you use a really short piece of hose, right? I think gas tanks today have a screen, so you can't siphon out. But all right, we'll stop at 22. I'll just hang in there. I know it's a long class, but just a few more minutes, really. I'm going to let you out a few minutes in a bit when I hand out your exam. Okay, V is right. No, V is right. So the length actually has quite a big impact on the flow rate. And that'll become important when we're talking about the, what's it called, the systemic versus the pulmonary. Because the systemic system is what? Is it longer or shorter than the pulmonary system? See, man, y'all know all sorts of stuff about this. I just learned this morning, like 10 minutes ago. The systemic is a lot longer than the pulmonary, right? Because the pulmonary just goes from the heart to the lungs, but the systemic goes all over the place. All right, we'll talk about that next time. All right. And then we have one final thing. I know y'all are getting sick of this, but the radius. So what if we make our pipe a lot narrower? Is that going to make it easier or more difficult? Y'all just yell it out loud. More difficult. Like if I have a really narrow pipe, it's going to make it a lot more difficult to push fluid through there. So, so we have Q is inversely proportional to L. That means that as L goes up, Q goes down. And then Q is directly proportional to R. That means if it gets bigger, that means that Q is going to get bigger. Let me extend this down a bit. All right, so we can put all these together and we get this equation. This is called Pascal's equation. It's French. I know I'm butchering it, but it looks like this. It's in your book. It's pi r to the 4th times my change in pressure over 8 eta L. Don't bother memorizing this equation. Like I'll probably just give it to you on the test actually. But I want you to know the different relationships. That for example, if I increase the radius of it, it's going to increase the flow rate. If I make my pipe bigger, it's going to be easier to push fluid through it, right? A bigger pipe is just easier. If I increase my pressure differential, it's going to increase my flow rate. If I increase my length, what's going to happen to my flow rate? It'll decrease, right? So if I make a longer pipe, then it's going to be harder to push fluid through, and so the flow rate will decrease. And then finally, if I increase the viscosity, likewise, going to decrease my flow rate. So if I'm trying to push water and then I try to push oil or maple syrup or whatever, I'm going to get a lower flow rate given all those other things the same. This is called Pascal's equation. P-O-I-S-E. Pascal's. No, it's Poiseuille. Poiseuille. Yeah, I did too. Destiny. Poiseuille. Can y'all say that? Poiseuille. You can't say it? It's Poiseuille. So at lunch today, you can talk about the flow of your Coke through your straw. Let me rewrite this. And it's called Poiseuille's equation. All right? Huh? Oh, it's part of the 4th, yeah. Okay, yeah, so one other thing here is notice the very strong correlation on R. So if, for example, we have Q is directly proportional to R to the 4th. So for example, if I make this bigger by a factor of 2, it's going to increase my flow rate by what amount? 16 by 2 to the 4th, because I have this 4th power. So any changes that I have in the size of the vessel, the pipe or whatever it happens to be, is going to change my my flow rate drastically because it has that fourth root in it, that fourth power. All right, next time we will pick up with applications to the body. The section is called Applications to the Human Body. So I have a lot to learn between now and then. But right now I'm going to hand back your, once you get your